In the last lecture on specific heats of gases, we have already seen that capital Cp, the molar specific heat of a gas at constant pressure, is defined as Tq at constant pressure by the number of moles times dt. And likewise, the molar specific heat, this should be capital C, mind you. The molar specific heat at constant volume is defined as dq at constant volume times n dt. We also saw that the difference Cp minus Cv is equal to the universal gas constant. The universal gas constant, you must be knowing, is 8.3 joules per mole Kelvin. Note how it has the same units as Cp and Cv. Now, another way to define the specific heats of gases, although it's not very commonly used, that would be the principal specific heats. So I've discussed this a bit in class, and the notation for the principal specific heats is using small letters, so Cp and Cv, and the only difference between the molar specific heat and the principal specific heat is the way that the normalization is done. The molar specific heat is got by dividing by the number of moles, whereas the principal specific heat is got by dividing by the mass. So this is going to be dq at constant pressure divided by the mass times dt, and likewise this is going to be dq at constant volume divided by the mass times dt. And just as Cp minus Cv is equal to capital R on this side, you get a similar relationship between Cp and Cv, the principal specific heats. So small cp minus small cv is equal to, on the right hand side, although you do not get the universal gas constant, you get a gas constant for the particular gas being used. I'll explain that in a moment, but the symbol is small r, and the units of small r are obviously going to be the same units as Cp and Cv, this Cp and this Cv. So it's going to be joule per kilogram Kelvin. So what is this small r exactly? It's not going to be used very often, but you should just know what it means. So just pay attention. To understand what this small r is, we just consider the gas equation, the equation of state, which is PV is equal to nRT. So that's an equation which is valid for all gases, oxygen, nitrogen, whatever. Now supposing that I write it in the following way, I write PV for a certain gas is, I don't want to write the number of moles, but I want to write the mass of the gas. It can be done. You write the mass of the gas over here. Now if you write small m, the mass of the gas, instead of the number of moles, then the constant which you write after m is not going to be capital R, but it's going to be small r, which is the gas constant for the particular gas. For example, small r will be different for oxygen, nitrogen, helium, and so on, and this I have to multiply by capital T. So to find out what exactly this small r is, you just notice that n into capital R must be equal to small m into small r. So I just equate them, and r is equal to small m into r, and I get small r for a particular gas is nr divided by m. Now let's go a bit deeper into this. The value of n is nothing but the mass of the gas in grams, well, that's going to be the mass of the gas in kilograms. Notice that this m is in kilograms. We are operating in the SI system. In this equation, for example, everything is supposed to be in the SI system as usual. So I'm assuming that the mass small m is in kilograms. So n, which is the mass in grams, is going to be m, small m, the mass in kilograms. When I multiply it by 1000, I get the mass in grams, and then I have to divide by the molecular weight. That's nothing but small n, the number of moles. Just check it again. M into 1000 is effectively it's the mass in grams. When I divide by the molecular weight, I get the number of moles. And now I just multiply this by capital R and I divide by small m. Notice how small m cancels. So I finally get small r, which is the gas constant for a particular gas, is 1000 multiplied by the universal gas constant divided by the molecular weight of the gas. So if I use this particular value for small r, then I can actually use this equation. So the product of the pressure and the volume is the mass of the particular gas in kilograms multiplied by the value of small r for that particular gas and multiplied by the absolute temperature. We will almost never use this. As I said before, we'll exclusively use this one, but you should just know this. Notice how small r, unlike capital R, is not a universal constant. It's because of the presence of this molecular weight over here. So for example, the value of small r for oxygen is going to be 1000 multiplied by capital R would be 8.3 SI units divided by the molecular weight of oxygen, which is 32. So this value of small r will work in this equation provided that the gas is oxygen. On the other hand, the molecular weight of nitrogen is 28. So to find small r for nitrogen, I have to divide by 28, and then I can use this equation for nitrogen. In other words, small r is not the type of universal constant which capital R is. In fact, small r is not a universal constant at all. It's a gas constant which we use for a particular gas. So I now turn to this equation. How come small Cp minus small Cv is equal to small r? So we can very easily prove that by starting from this equation, Cp minus Cv equal to capital R. I'll just rewrite that over here. Cp minus Cv is equal to capital R. And now in place of Cp, I'm going to write the corresponding expression which contains small Cp. So there is a relationship between this Cp and this Cp. Just divide one by the other and you'll easily get the relation. So I think I'll just write it over here, this place over here. So capital Cp divided by small Cp is equal to the dqp and dt terms will cancel, and what I get is the mass of the gas in kilograms divided by the number of moles, which is nothing but the mass of the gas in kilograms divided by n is the mass of the gas in grams divided by the molecular weight. So that's going to be the molecular weight multiplied by the mass in kilograms divided by the mass in grams. So if it's 1 kg up here, it's going to be 1000 kg down here, so I have to divide by 1000. So this is capital Cp divided by small cp. So I just simplify that. I get capital Cp is equal to molecular weight divided by 1000 multiplied by small cp, sorry. So that's what I am going to use in this equation. I substitute for capital Cp. I get molecular weight upon 1000 multiplied by small cp, and likewise I get, in place of capital Cv, I can write the molecular weight multiplied by small cv divided by 1000, and that's equal to the universal gas constant R. Now if I take these thousands on the other side and likewise the molecular weight of the gas on the other side, I get Cp minus Cv is equal to 1000 times capital R divided by the molecular weight, and according to this equation this is nothing but small r. So in other words, if I use small Cp and small Cv, in other words, if I use the principal specific heats of a gas, then the relationship is their difference, that is Cp minus Cv, is not equal to the universal gas constant, capital R, but rather it is equal to the gas constant for that particular gas. In other words, it's equal to small r. Now the next point that we will see is again something that we did discuss in the previous lecture, namely that the change in the internal energy of a gas is actually equal to n times the molar specific heat at constant volume multiplied by dt. I'll just revise how come this equation is valid. So remember, we discussed in class that if you keep the volume of a gas constant and you supply it heat from outside, let's say it's dq, so this is heat supplied at a constant volume, and that's going to be, by definition, that's going to be n times Cv multiplied by dt. And we know, according to the first law of thermodynamics, that dq is equal to the change in the internal energy plus the work done by the gas, which is equal to 0 in this case, so I need not write this. So from this equation we get the equality of these two. In other words, whenever the temperature of a gas, whenever the temperature of a gas increases by dt, we know that the internal energy of the gas is going to increase by an amount which is equal to n Cv dt. So you see that the change in the internal energy is basically a function of change in temperature, or in other words, internal energy is a function of temperature of the gas, apart from the values of Cv and n, of course. So that's one equation that you already know probably, and you must memorize that if you haven't yet. Now this equation is transformed into an absolute equation by doing an integral, and what we get is delta E internal is equal to NCV delta T. It's easy to see what these two equations mean. If I plot a graph in which I have E internal on the y-axis and I have the absolute temperature on the x-axis, then dE internal divided by dt is equal to NCV, which is a constant for a particular mass of a particular gas, and that's also the same as delta E internal divided by delta T, that's also equal to NCV. In other words, you're going to have a straight line having slope equal to NCV, positive of course, when I actually plot, or when I actually write E internal as a function of the absolute temperature of a given mass of a gas. Now the graph that we have drawn implies that at a temperature of 0 Kelvin you have some positive internal energy. On the other hand, I could have drawn a graph of that nature where the assumption is that at 0 Kelvin you have a negative value of the internal energy. Now it so happens that by convention it's assumed that the internal energy of an ideal gas is exactly equal to 0 when the temperature is 0 Kelvin, and that means that must draw a line which is parallel to the remaining two passing through the origin. That's a convention, and we are allowed to adopt the convention because of the fact that the internal energy consists of internal kinetic energy plus internal potential energies. Now in classical physics, at 0 Kelvin the kinetic energy of the gas molecules, the internal kinetic energy, is actually equal to 0. That's according to the classical theory. And the other term is a term whose datum we can define as we want. There is no restriction on that. So because you can define the datum of the potential energy as you want, you can always manipulate the potential energy formula by adding a constant to it, and what would happen, the implication is that you can manipulate the datum of potential energy. So the sum total of kinetic and potential internal energies is equal to 0 when the temperature is 0 Kelvin. So in other words, at 0 Kelvin, you know for a fact that in classical physics, the internal kinetic energy, the microscopic kinetic energies of the gas molecules turn out to be 0 according to classical physics. So all you have to do is to define that the internal potential energy of the molecules of the gas is equal to 0 when the temperature is 0 Kelvin. That's an arbitrary definition, and once you define it that way, you get the result that at 0 Kelvin the total internal energy of the gas is 0 in kinetic plus 0 in potential, so that's equal to 0. That's how this line actually passes through the origin. Okay, now what this means, if you look at this equation carefully, supposing that delta E internal you measure with respect to the origin, and delta T also you measure it with respect to T equal to 0 Kelvin. So it's going to be E internal minus 0, the left hand side, is equal to NCV times capital T minus 0. So naturally I get a formula which actually is not unexpected, because the equation of such a line is of the form y equal to mx. So what I get is E internal is equal to N times CV times T. That's the formula for the internal energy of an ideal gas at temperature equal to capital T. So the difference between this version over here and this version over here is that in the second version we are actually talking about the absolute internal energy of the gas, whereas in the version over here as well as over here we are talking about the differences in the internal energy. So if you ask me the absolute internal energy, the second formula, E internal is equal to NCV into T, is more widely used than the difference formulae, and the difference formulae can easily be derived from the absolute formula. So I would suggest that you remember the absolute formula. In other words, you remember that the internal energy of an ideal gas is always given by N times CV times T, and then if you differentiate this, you could always get the difference formulae, or if you put the delta sign in front of the LHS and the RHS, then you get the difference equation. So that's the internal energy of an ideal gas. So just to briefly revise what we have done up till now, we have defined Cp, we have defined Cv, we have defined small cv and Cp2, and we have said that we have proved that capital Cp minus Cv is equal to capital R. We did prove a similar relationship between the small cp minus small cv is equal to small r, and we said that the internal energy of an ideal gas is defined by N times Cv multiplied by the absolute temperature, and therefore the change in the internal energy, small change, large change, it doesn't matter, it's going to be N times Cv multiplied by the change in temperature. Here too it's going to be N times Cv multiplied by the change in temperature. More or less this is what we have seen. Now just as an interesting point, if I ask you what is C isothermal, they may ask you such a question in the JEE main. It's a common sense question. So you know that you have C at constant volume, you have C at constant pressure. In other words, if you keep the gas volume constant, that is in an isochoric process, you get a certain value of C, which is called CV. In other words, if you on the other hand, if you keep the pressure of the gas constant and the process is isobaric, then you get a certain value of C, which is called Cp. Now what happens if you don't actually allow the temperature of the gas to change at all? So it's called an isothermal process, as you know, and the definition of isothermal C must be dq divided by dt multiplied by the divided by the number of moles, and this dq is the heat which is applied in an infinitesimal step, assuming that the temperature doesn't change because it's isothermal. So you notice that the denominator is actually equal to 0. So this means that nominally you get a value of infinity over here. So C isothermal, one can say it is equal to infinity. Similarly, C adiabatic. So C adiabatic, C adiabatic. So in other words, you create, or you allow the gas to go through an adiabatic process in which no heat is exchanged with the surroundings and its temperature rises by dt. So your C adiabatic is going to be dq by n dt, and naturally, since dq is equal to 0, you get C adiabatic is equal to 0. Just a bit of common sense. So how would you actually change the temperature of a gas in an adiabatic process? Is it possible, or is the dt going to be 0 too? I'll just show you why it's not going to be 0. So you have an adiabatic enclosure like that. That's also adiabatic. You have a piston which is adiabatic, and unlike the diagram in RHK, I'll just enclose the gas completely by an adiabatic enclosure, and you have a pile of sand on top of this, etc. Now let's see how you can change the temperature of this gas simply by manipulating the pressure. So let's say if you add more sand to this, the piston is going to go down like that gradually. So you get a compressed gas over here, and in doing so you actually change the temperature of the gas. That's because of the following logic. If you apply the first law of thermodynamics, the heat supplied to the gas is equal to 0, and the work done by the gas is negative, so naturally delta E internal must be positive. So that implies that if you adiabatically compress a gas, then you're going to increase the temperature of the gas because you increase the internal energy. So in other words, you can actually have a positive value of dt even though dq is equal to 0, and that means that the adiabatic specific heat of a gas is actually equal to 0. We now describe some details of a particular type of process called a reversible adiabatic process. You are aware that an adiabatic process is one in which the gas or the system is not allowed to exchange heat with the surroundings. So you could just imagine that there is an adiabatic enclosure like that. So these walls are adiabatic, and the gas over here, on the top of the gas there is a piston which is also adiabatic, and you could change the pressure by adding or removing grains from this pile of sand. So the state of the gas is essentially changed by manipulating this sand. You're not allowed to pass heat into the gas to give heat to the gas or to remove heat from the gas. So that's how you should visualize an adiabatic process. Now what we will do in this section is to try and find out how an adiabatic process looks like on a PV diagram. That's one thing we'll do. Another thing is we'll try to establish relationships between the variables pressure, volume and temperature in an adiabatic process. Now I want you to imagine that a certain gas, an ideal gas, is undergoing an adiabatic process, and we are now going to apply the first law of thermodynamics to a small step of the process. So in the differential form, the first law is written as follows: dq, which is the small amount of heat supplied to the gas, is the work done by the gas on the surroundings plus the change in the gas, in the internal energy of the gas. Remember, we are describing a small step of an adiabatic process, and because of that, you know that dq, the heat provided to the gas from the surroundings, must be equal to 0. Likewise, the work done by the gas on the surroundings in a small step is nothing but P times dV, where P is the pressure of the gas and V is the volume, so dV is the change in volume. And finally, the change in the internal energy of the gas is going to be the number of moles of the gas times the molar specific heat of the gas at constant volume times the change in the absolute temperature. Now, our objective in this initial procedure is to establish a pressure versus volume relationship for an adiabatic process. In other words, we are going to get a differential equation from this involving only the variables pressure and volume, and so we want to get rid of the dt, the temperature term. Don't lose sight of the logic of the proof, and then the proof becomes relatively easy, otherwise it's quite difficult to follow. Now, to get rid of the temperature term, I write the ideal gas equation of state, that is PV is equal to N times R times T, and I actually want to substitute for dt, so I differentiate this. I get PdV plus VdP is equal to N times R times dt. Now after you substitute for dt, in fact you could substitute for N multiplied by dt in place of the N times dt over here. After you do that, and after you simplify things, what you get is this CV plus capital R times P dV plus CV times V dP is equal to 0. And you know that the CV plus CR, that expression is actually equal to CP, because CP minus CV is equal to R. So I'll just rewrite that CP multiplied by P times dV is equal to, I'll take this second term on the other side, minus CV into V times dP. Now the ratio of CP and CV, in other words CP divided by CV, is usually denoted by the symbol gamma. So I just take CV down there and I get gamma times dV upon V, of course I have manipulated some terms, is equal to minus dP upon P. Notice how I've got a differential equation involving pressure and volume only. The temperature term is out of the equation as required. Also notice that gamma is a constant, so there's no variable there. And all I need to do now is to integrate this. I hope you have noticed that the variables have been separated. So on the left hand side I've got the volume variable, on the right hand side I've got the pressure variable. So upon integrating this between the initial values and the final values, what I get is gamma times the natural logarithm of V final upon V initial equals minus of the natural logarithm of P final divided by P initial, and the gamma I can take inside this log, so V final raised to gamma upon V initial raised to gamma. Further, the right hand side I can just take the reciprocal of what appears after the log in order to get rid of the minus sign. So I'll just write a plus over here, and here I'll write P initial, whereas here I'll write P final. Now take the antilogs. So the antilog on the left hand side is simply going to be V final raised to gamma divided by V initial raised to gamma. In other words, I just remove the log sign. Likewise, on the right hand side I remove the log sign. So I get this relation, and after cross multiplying, what I get is P initial times V initial raised to gamma equals P final times V final raised to gamma. So we started by assuming that a gas was undergoing an adiabatic process. We wrote a differential equation for a small step of that process, and then we solved the differential equation, and we got a relationship between the initial and final values of pressure and volume in that whole process, and the final pressure and volume for that same process. And gamma is the ratio of specific heats, that's Cp by Cv. So this is true for any adiabatic process. So if you have a process which is the physical process is described by that diagram which you see over here, you could say that P times V raised to gamma is never going to change for that particular process. It's equal to a constant. Or you could say P1 V1 raised to gamma is equal to P2 V2 raised to gamma. That's another way of saying it. Now you know that gamma is a positive constant. So and in fact it is larger than 1. Cp upon Cv, well, it's a positive constant. Cp is larger than Cv, so obviously gamma must be larger than 1. There is some sort of inverse proportion, isn't it, between P and V. It's not exact inverse proportion. It would have been inverse proportion if gamma was equal to 1, which it can't be, of course. But still, you know that as P increases, you know that V decreases. And if P decreases, you know that V increases. So if you actually use calculus and try to plot the curve, you'll find that it is asymptotic to both axes, and the graph would look a bit like an isotherm, something like that. So that's an adiabatic process whose equation is given by P times V raised to gamma is equal to constant. Adiabatic process for a certain mass of a certain gas, and the gas is assumed to be ideal because in the derivation we have used the equation of state for an ideal gas, this equation over here. So remember what we set out to do. We wanted to draw a graph of an adiabatic process, which we have already done, and we wanted to establish relationships between P, V and T, and we already have one between P and V. Now to get the relationship between the volume and the temperature, or between the pressure and the temperature, you just need to eliminate the appropriate variables. For example, you can choose to eliminate the volume using the ideal gas equation in the form V is equal to nRT divided by P. So you get rid of V by substituting nRT upon P. In other words, you get an equation linking the pressure and the temperature. Now note that the number of moles is a constant for a given mass of a given gas, and R is also a constant. So all the constants, you can take them to one side of the equation, and the variables, which would be temperature and pressure, you keep them on the left hand side. So after some manipulation, what you get is P raised to 1 minus gamma multiplied by T raised to gamma is equal to a constant. I'll just reiterate that this constant would also contain R and N in some form. Those have been taken to the right hand side. So that's the equation connecting P and T. And likewise, you can write an equation linking volume and temperature by eliminating pressure, of course using the ideal gas equation in the form pressure equals nRT divided by volume. And once again you treat N and R as constants and take them to the right hand side of the equation, and finally you get an equation which is T times V raised to gamma minus 1 equals constant. It's worth doing these two proofs in your book after assuming PV raised to gamma is equal to constant. Now if you have memorized these three separate equations in chemistry, that's great. But if you don't want to memorize, if you haven't memorized them already, and if you find it difficult to memorize three separate equations, what you could do is to memorize one of them and derive the remaining two. For example, you could memorize PV raised to gamma is equal to constant, and using the gas law, ideal gas law in this form or in that form, you could eliminate either V or P as we just now did, and you could derive the second or the third equation as and when required. We now attempt to derive a formula for the work done by a gas in an adiabatic process. Imagine that in a certain adiabatic process, a certain mass of a certain gas changes from a state P1, V1, T1 to a final state P2 and V2 and T2. The process, remember, is an adiabatic reversible process. Now the work done by the gas during this process is of course going to be integral P dV from the initial to the final state. Now we use the fact that the process is adiabatic and the product of P into V raised to gamma is a constant. Let's call that constant K. And we're going to actually integrate this by expressing P in terms of V, because we need only one variable over here. So P is K divided by V raised to gamma. I write this equation in that form. Notice how the limits are the initial volume V1 and the final volume V2. Now upon integrating this, you get 1 upon 1 minus gamma times k upon v2 raised to gamma minus 1 minus k upon v1 raised to gamma minus 1. Now k divided by v raised to gamma from this equation, k divided by v raised to gamma is equal to p, and I've got k upon v2 raised to gamma minus 1. So I'll bring v2 raised to gamma in the denominator by multiplying this by v2, and obviously this 1 will go away, and likewise you multiply this by v1 and make this 1 go away. So you have now the work done in an adiabatic process by a gas, an ideal gas, to be 1 upon 1 minus gamma. Now k upon v2 raised to gamma, as described previously, is nothing but P2. So P2 V2, the product of the final pressure and volume minus the product of the initial pressure and volume. So that's the work done by the gas in a reversible adiabatic process. Now usually I tend to reverse the order of the terms in the denominator, and that's all that is up to you. I write it as 1 upon gamma minus 1 because gamma is larger than 1. Cp by Cv is larger than 1, as Cp is larger than Cv. So I tend to make the denominator positive like that. I'm just more comfortable with that. And up here I write P1 V1 minus P2 V2. Now the problem about making the denominator positive is that in the numerator you get the initial product, the product of the initial pressure and volume, that's the initial, minus the final product, and that's not usually the way we write formulae. Usually it's final minus initial, because usually we are talking about changes. So it's up to you how to memorize the formula. If you want to have a positive denominator and you want to write gamma minus 1 there, then make sure that you write the numerator as the initial product of PV minus the final product. Now if I go back to my graph over there, which describes an adiabatic process, and I link it with the work done. Remember, the work done is integral P dV, and we have simplified that and we have got that formula. But essentially the work done is nothing but the area underneath that graph. So let's imagine that the initial state is over here, state 1. So for example, that would be pressure P1, that would be pressure P1, and that would be volume V1. And likewise imagine that state number 2 is over here, so P2 and V2 would or V2 and P2 would be the coordinates of that point 2. So you can see that the gas has actually gone along this curve in this direction, like that, from 1 to 2, and the pressure the area underneath the graph is this area, which we know to be positive. We treat that area as positive, as discussed earlier, because the whole process goes from left to right, and it's an expansion, mind you, because V2 is larger than V1. So you can see that in an adiabatic expansion, the work done by the gas on the piston or on the surroundings is bound to be positive, which would mean in this form of the equation, see, gamma minus 1 is anyway positive, but it would mean that P1 V1 must be larger than P2 V2, because you need the work done to be positive in an adiabatic expansion. It's not very obvious from the graph that P1 V1 is larger than P2 V2. Not very obvious. For example, at point number 1 you have a large pressure as compared to point number 2. That's good. But you have a small volume as compared to point number 2. So it's not very obvious that P1 V1 is larger than P2 V2, but it is. By inference, it is. So in an adiabatic process, the work done by the gas is positive, and in the formula, the bracketed term over here has to be positive. And how do you accomplish an adiabatic expansion? So you go back to this diagram and you just remove the sand or a part of the sand bit by bit or grain by grain, so that the gas actually expands and you get an adiabatic expansion. Now the reverse is true for an adiabatic compression, in which you keep on adding grains slowly one by one and stopping after adding every grain for the gas to settle down. In that case, what will happen is the direction of the process in the diagram would be reversed. It would be that way. So 1 would be lower down compared to 2 on the graph, and the area would be then treated as negative because you're going from right to left, and in that case, of course, this thing would be negative. So that's just I'm trying to link the equation with the graph with the physical diagram, so that you get a certain level of comfort with adiabatic processes. Now we did say earlier on that in standard processes like isothermal and isobaric and so on, the work done by the gas would almost always have two different equations which say the same thing, but they look different. So for example, the work done in an isothermal process is nRT ln V2 by V1, or it's also nRT ln P1 by P2. Now the same is true for an adiabatic process, because the work done is P1 upon gamma minus 1 P1 V1 minus P2 V2, but we can use the equation of state for an ideal gas, which says that PV is equal to nRT, and therefore it would mean that delta of PV is equal to delta of nRT, or if you want, you could write it as nR delta T, because N and R are constants. Now delta of PV is the change in the product, so it's P2 V2 minus P1 V1, which you can actually substitute in that equation. You get a minus sign, of course, there, so 1 upon gamma minus 1 into minus of nR delta T. That's an alternative form. So the work done by a gas on the surroundings in an adiabatic process has two formulae. Both of them are equally correct. The first one involves the pressure and volume. The second one involves the temperature. You have to choose the appropriate formula depending upon the data. Now there's something very interesting you can do with the result of the work done. And to begin, I just tabulate this thing. So in an adiabatic process, the equation which is always satisfied is P into V raised to gamma is constant, and the work done by the gas has these two equations. Now notice that gamma, which is Cp by Cv, has certain specific values. Later on in the chapter we'll learn that in an ideal monatomic gas, gamma is 3 by 2, 1.5, or in an ideal diatomic gas, gamma can actually be 5 divided by 3 under certain conditions, of course, and gamma for a diatomic gas under some other conditions can actually be 7 divided by 5. So gamma would be a constant for a gas under certain conditions. It's going to be treated as a constant for a given process. Now supposing that you have a process whose equation is P V square equal to constant. Now this is not an adiabatic process. There is no gas for which gamma is actually equal to 2. But the fact remains that you could subject a gas to this sort of process. Why am I so confident about that? If there's going to be some diagram corresponding to this PV square is equal to constant, right? If I give you the value of the constant, you'll be able to plot this graph. I think it's going to be some sort of graph which looks like that. Now, you're basically taking the gas from this point to the next point to the next point to the next point to the next point by carefully manipulating the pressure and the volume. It can be done, of course. Okay, think of the apparatus which I gave you, the RHK apparatus, by which I mean the figure which I'm just drawing right now. So it's self-explanatory, right? I don't have to describe that apparatus. So if you want to achieve, let's say that the gas is at a certain volume, a certain pressure, and naturally a certain temperature, and you want to change the pressure and the volume to certain known values. So the first thing you could think of is to adjust the number of grains of sand at the top so that you get the required pressure. And when you do that, of course, the gas temperature is going to change, the volume would change, the temperature would also change. The next thing that you do is to adjust the temperature slightly. You would either increase it or you would decrease it, which would change the volume too, until the volume reaches the appropriate value. So these would be two infinitesimal steps in succession. The first thing is to manipulate the grains of sand to get the required pressure. You may not get the required volume in that step. If you do, you are lucky, but you might not. So then you manipulate the volume indirectly by manipulating the temperature, by changing the temperature by an infinitesimal amount. And that's how you can get from that place to that place to that place to that point. You can actually make the gas travel along that PV diagram. So PV square is constant, is a process. It's not adiabatic, but it is some process. Now, the work done by the gas when following the process PV square is equal to constant. You can directly write the formula if you remember these two formulae. You just compare PV raised to gamma is constant with PV square is equal to constant, and just go through the proof of the adiabatic work done, and you realize that in the proof we did not put any conditions on gamma. Gamma was just treated as some constant, Cp by Cv, fine, but the proof doesn't say that gamma should be Cp by Cv. So essentially what you have done is you have found the work done by a gas which is following the process PV raised to gamma is constant, where gamma is some constant. It doesn't matter if gamma you put it as 2. Well, gamma can't be 2, but if I say PV square is equal to constant, the only thing that's going to change in this proof is in place of gamma you're going to write 2 everywhere. So in other words, the final results are true if you put gamma equal to 2. So PV square is equal to constant. If you are ever given a process like that, it's very difficult to describe that process. It's not a simple process. It's neither isothermal nor isobaric nor adiabatic. But you know what is the work done without actually going through the derivation. It's going to be P1 V1 minus P2 V2 divided by 2 minus 1. So 2 minus 1 is of course 1, or it's going to be minus of n r delta T upon 2 minus 1. Mind you, it's not an isothermal process. It's not an isobaric process where you have a somewhat similar formula, but with the difference in sign. The work done by the gas in an isobaric process is nr delta T, or it's delta PV, whereas here you've got minus of delta PV. But that's not the point. The point is, whatever be this number over here, you can easily use the analogy with an adiabatic process, you substitute in place of gamma, you write whatever number is over here and you get the work done. And of course there's one exception. In the proof there is an explicit assumption that gamma is not equal to 1, otherwise the denominator here would actually become 0. That's not allowed. So unless you have a case where that number is 1, in other words, we'll write the only exception over here, PV equal to constant. PV raised to 1 is equal to constant. Apart from that case, this formula these formulae will work for any value of gamma, even if it's not the ratio of specific heats, it's any arbitrary number like 2, 3, even negative numbers or fractions would do. Now the thing that I just discussed, how to find the work done in case a gas follows a reversible process, which is described by PV raised to 2 equal to constant, or in fact PV raised to K equal to constant. I'm not sure that formula is actually present in the handout, although the formula for PV raised to gamma is equal to constant, the work done is present. So I just request you to add the formula to the handout, and you could write the following. In case an ideal gas is taken through a process described by PV raised to K equal to constant. Now K could be gamma, of course, but of course there's one condition: K should not be equal to 1. So that's the only condition which we have to impose. Then the work done by the gas on the surroundings is given by P1 V1 minus P2 V2 upon K minus 1, where P1 V1 are the initial values of pressure and volume, and P2 and V2 are the final values. And of course you could write it in terms of the temperature as follows. So it's equal to minus N into R into delta T upon K minus 1. So just insert that in your handout at an appropriate place, maybe at the end or wherever you have space. And now we can proceed. Now coming back to this PV raised to 1 is equal to constant, it's not much of a disadvantage not being able to use the formula for PV raised to 1 is equal to constant, because PV raised to 1 is equal to constant, which means PV is equal to constant, is nothing but an isothermal process, and you know already the formula for the work done by an isothermal process to be nR2 ln V2 by V1 or nR2 ln P1 by P2. So you know a formula for this, use that formula, and in all other cases use this formula or this formula or a formula similar to that, depending on the value of the power of V. So that's something that you ought to bear in mind. Don't derive the formulae like this by first principles. You just write the work done by analogy with an adiabatic process. That's what I want to say. The values of Cp and Cv are fixed for a given type of gas. For example, for a monatomic gas, assuming it is an ideal gas, of course, the value of Cv is 3 upon 2 R, and the value of Cp automatically gets defined because it's equal to Cv plus R, so it turns out to be 5 upon 2 times R. In this part of the chapter, we are actually going to derive why you get fixed values of Cv and Cp depending on whether the gas is monatomic or diatomic and so on. And the basis of the derivation is a theorem which we will not prove. It's called Maxwell's law or Maxwell's theorem of equipartition of energy. The law or the theorem of equipartition of energy can be understood once you understand the concept of degree of freedom. So the degree of freedom is the number, it's an integer, a positive integer. It's the number of independent ways in which a gas molecule can possess energy. Now in the hypothetical, hypothetically, a gas molecule is assumed to consist of atoms which are hard and tiny spheres. So this would be the picture of a monatomic gas molecule in this theory. And of course the dimensions of this sphere would be very, very small, much smaller than what I've drawn. A diatomic gas molecule would of course have two tiny hard spheres, and there would be forces between them somewhat similar to the spring forces. So that's actually one molecule, a diatomic molecule. Now let's talk about a monatomic gas like helium first. If I ask you to describe the energy of the molecule, it's going to have only kinetic energy, because the potential energy of interaction between two separate helium atoms or monatomic atoms is assumed to be negligibly small, and the reason is that the distance between them is too large in the case of a gas for there to be any appreciable interaction between two separate molecules like that. So the only type of energy which a monatomic gas molecule can have is kinetic energy. Now the velocity of a particle like that will have three components: Vx and Vy and Vz, and that's the formula for the vector velocity of that particular particle or monatomic atom. And obviously Vx and Vy and Vz are independent of each other. In other words, you can have any value of Vx independent of the value of Vy and also independent of the value of Vz. Now the kinetic energy of this monatomic gas molecule, which is half mv square, which can be written as half mv bar dot v bar, and if you just do the computation, it's going to be half m into Vx square plus half m into Vy square plus half m into Vz square. So taking this argument of the independence of Vx and Vy and Vz one step further, you can see that you have three energies corresponding to the three motions in the three directions. So half mvx square and half mvy square and half mvz square are three independent energies. In this case they are kinetic energies which a monatomic gas molecule can possess, and since they are this number 3 is called the degree of freedom of a monatomic gas molecule. So the degree of freedom of a helium molecule is 3, because there are 3 independent ways in which the helium molecule can possess energy. Similarly, the degree of freedom of a neon molecule, which is the same of course as a neon atom, is once again 3, because of the presence of exactly 3 independent contributors to the total energy of the molecule. Now what Maxwell said is, let's talk about the application of his theorem. By the way, Maxwell was a Scottish physicist, and this was one of the areas he contributed in. He also, it's the same Maxwell who gave us the laws of electromagnetism, the 4 Maxwell's laws. So he has contributed to the science of thermodynamics too. So let's try to apply Maxwell's theorem to a monatomic gas. So what the theorem says is that if you consider a gas molecule a single gas molecule. Okay, then on an average, this is very important, there's some averaging process going on. On an average, the gas molecule will have an energy which is given by half times K times T multiplied by the degree of freedom possessed by the gas molecule. Now T is the absolute temperature of the gas, and K is a constant called the Boltzmann constant. Boltzmann constant can be viewed as being the gas constant for a single molecule. So what do I mean by that? Thing is not clear at all, I'm sure. So Boltzmann constant is actually equal to the universal gas constant divided by the Avogadro number. So Boltzmann constant is R upon N naught, and the value of Boltzmann constant can be found from standard books to be equal to very nearly 1.38 multiplied by 10 raised to minus 23 joules per Kelvin. That's the value of Boltzmann constant. Now let's apply this theorem to a monatomic gas molecule. So actually every monatomic gas molecule at a given temperature will not possess the same amount of energy. Let's be clear on that point. There is going to be some sort of distribution, and we are talking about the average energy. Be very, very clear about that. The average energy possessed by a gas molecule in a monatomic gas is going to be half kT. So that's sometimes said to be the energy, the average energy per degree of freedom. And I must multiply this now by 3, because there are 3 degrees of freedom for a monatomic gas molecule, and so that turns out to be 3 by 2 K times T. Now how does this help us to find the value of CV and CP for a monatomic gas? So this is the average energy possessed by a single gas molecule of, let's say, helium or neon, monatomic gases, that is. Now when I multiply 3 by 2 kT, the energy per molecule, with the Avogadro's number, which is essentially the number of molecules in 1 mole, then naturally I get the energy per mole, the internal energy per mole. I'm talking about the internal energy, of course. And the multiplication of K and N naught by definition is equal to the gas constant. So the internal energy of monatomic gas per mole is 3 by 2 multiplied by R multiplied by T. Or if there are N moles of a monatomic gas, then the internal energy of the monatomic gas is given by 3 by 2 multiplied by N multiplied by R multiplied by T. And we have seen earlier that that there is a relationship between the internal energy of a gas and its molar specific heat at constant volume. So I'll just revise that for you. If you have got a gas in a fixed container whose volume isn't changing, and let's say that you heat the gas, you supply heat from outside in that direction, so the heat which you supply, let's call it dQ at constant volume. Now since no work is done at constant volume, this heat completely goes into raising the internal energy of the gas. So on the right hand side I have got dE in. Now this dQV is nothing but the number of moles times the specific heat of the gas at constant volume multiplied by dt. That's the definition of CV. CV is dqv upon n dt. So I equate this to dE in, and what I get therefore is n times CV times delta T is equal to delta E internal. So you can see that the temperature versus internal energy graph is actually a straight line, because delta E internal divided by delta T, that's going to be n times CV, which is a constant. Now the assumption made is that the internal energy is 0 when T is equal to 0. So that's the simplest possible linear equation that you could get containing T and E in. And in that case, I get E in is equal to n times CV multiplied by the absolute temperature T. Notice how this equation is consistent with the assumption that the internal energy of a gas is 0 at 0 Kelvin. So I'll just rub this out, and I'm going to put that equation, I'm going to use that equation over here, where we proved that the internal energy of a gas at an absolute temperature of T is 3 by 2 RT. So equate that, or for n moles of a gas, did I rub that out? No, it's over here. The internal energy of n moles of a gas is 3 by 2 nRT. Now you equate that to n times CV times T, and these things just cancel, n cancels, and you get the result that the specific heat at constant volume for a monatomic gas is 3 by 2 times R, and Cp, which is CV plus R, turns out to be 5 upon 2 multiplied by R. And finally, gamma, which is the ratio of specific heat Cp by Cv, turns out to be 5 upon 3. So that's how to derive the values of Cv and Cp and gamma for a monatomic gas using Maxwell's theorem of equipartition of energy. Now, how is it applicable to diatomic gases? A diatomic gas, as I said earlier, is visualized as two particles connected by a spring, one could say, or two particles, and there is a force between them. There could be a force of attraction or repulsion depending on whether the particles are brought closer or to each other, or whether they are separated from each other. It acts like a spring. Now, if I treat the system as a single system, then it again has three kinetic energies of translation depending on whether the whole system or its CM is moving in this direction or this direction, etc. So there are three translational degrees of freedom corresponding to the CM's velocity along the x direction, the y direction, and the z direction. So we are talking about half mvx square and half mvy square and half mvz square. Now in addition, there's going to be a rotational kinetic energy. So for example, if that's the x-axis, then it's possible that this molecule, diatomic molecule, is rotating about the x-axis. Notice that the x-axis, for simplicity, I've shown it passing through the midpoint. It should actually pass through the CM of these two. So these two rotate about it like that. Okay. So there's going to be a rotational kinetic energy, which is a force given by half Ix times omega x square. So there is one independent rotational degree of freedom, and just as there's a rotational degree of freedom about the x-axis, you could do the same thing for the y-axis. But hold on, I just realized that this diagram may not be very clear to some of you. I'll just explain what I mean. See, this is the x-axis. The dotted line I've drawn is the x-axis, and imagine this dumbbell shaped figure rotating about the x-axis. It's very difficult to draw the arrows, but this particular particle right now is coming towards you, and this particle is going away from you. So it's a bit like, say they're moving along this circle like that with an angular velocity of omega x, and that's where I got this equation from. Now similarly, if I draw those two atoms again, I can have a similar rotational kinetic energy about an axis which is perpendicular to the plane of the computer screen, isn't it? So these particles will actually be moving in a circle like that, and if that's the y-axis, then the kinetic energy associated with that is half Iy into omega y square. So you have plus one more degree, rotational degree of freedom. And the z-axis, which passes through the molecules, doesn't contribute to any extra kinetic energy, because even if I apply the formula half Iz omega z square, which is the rotational kinetic energy about the z-axis, you see that the individual atoms are so small that they are effectively particles, almost particles. So the angular so the moment of inertia about the z-axis is actually going to be 0, because the particles lie on the z-axis. So this term is always going to be equal to 0. So the only two terms, I get two more terms, that is for rotation, and up till now I've got a degree of freedom of 5. Now there are two more degrees of freedom which you could consider, and in a moment I'll tell you why these are not usually considered at ordinary temperatures. So this molecule can also possess energy by virtue of the oscillations, that's like a spring, correct? So imagine that the spring gets alternately compressed and extended. So there is a kinetic energy and a potential energy associated with the vibration of this spring, and those are obviously independent of each other. So you get two terms, two degrees of freedom. One is kinetic and one is potential. Those correspond to vibrations. So let's count. You have 3 translational, 2 rotational, and 2 vibratory degrees of freedom. So one would expect that the degrees of freedom for a diatomic gas molecule is 7, whereas the degrees of freedom for a monatomic gas molecule, already we have proved it, is equal to 3. Now it so happens that at room temperatures, this effect, at moderate temperatures, this effect is absent or negligible. The vibratory degrees of freedom, they manifest themselves significantly only at high temperatures. So for most of our problems, we'll be assuming that the degree of freedom of a diatomic gas molecule is equal to 5 by neglecting the vibratory modes of freedom, and only if it is specifically stated that the temperature is very high, or if it is specifically stated that we have to consider vibration also, then the degree of freedom is equal to 7. So what happens if the degree of freedom is equal to 3? Let's go through that again. The value of Cv is 3 by 2 r, the value of Cp is 5 by 2 r, and the value of gamma is 5 upon 3. On the other hand, if the degree of freedom is equal to 5 for a diatomic molecule like hydrogen or nitrogen, so that's true for moderate temperatures, then the value of Cv becomes 5 by 2r. Well, it's because the average kinetic energy of a diatomic gas molecule will then be 5 upon 2 into kT, half kT per degree of freedom multiplied by 5, and then you do the same derivation and you get 5 by 2r as Cv, 7 by 2r as Cp, 7 by 5 as gamma. And at very high temperatures, the degree of freedom of a diatomic gas molecule is equal to 7. So these values become 7 upon 2r and 9 upon 2r respectively, and the third value becomes 9 upon 7. Gamma is equal to 9 upon 7. So just remember the derivation. Above all, remember the degree of freedom, how to judge the degree of freedom, and you should not go wrong in problems. That's partly because you now know the derivation of CV and CP, and you would therefore put in the right values of CV and CP in the problems.